Hi guys, in this video, we will discuss about the introduction to algorithms. So, do you have any idea about algorithms? First, let's start with the definition of algorithms. An algorithm is a procedure to accomplish a specific task. It is the idea behind any computer program. An algorithm is a finite set of instructions which, if followed, accomplish a particular task. In addition, every algorithm must satisfy the following criteria. First, we have finiteness. If we trace out the instructions of an algorithm, then for all cases, the algorithm will terminate after a finite number of steps. Then secondly, we have definiteness. Each instruction must be clear and unambiguous. Then, we have input. Valid inputs are clearly specified. Then output can be proved to produce the correct output given a valid input. And lastly, we have the effectiveness. Every instruction must be sufficiently basic that it can, in principle, be carried out by a person using only pencil and paper. It is not enough that each operation be definite, but it must also be feasible. So let's proceed with the historical perspective of the algorithm. In 300 BC, the Euclidean algorithm, procedure for finding the greatest common divisor or the GCD of two numbers, described by the Greek mathematician Euclid in his Elements. The method is computationally efficient and with minor modifications is still used by computers. The algorithm involves successively dividing and calculating remainders. The Euclidean algorithm is useful for reducing a common fraction to lowest terms. Another historical perspective is in the 9th century. Muhammad ibn Musa al-Khwarizmi principle states that all complex problems of science must be and can be solved by means of 5 steps. This is his most recognized work, which is named after him, the mathematical concept algorithm. The modern meaning of the word relates to a specific practice for solving a particular problem. Today, people use algorithms to do addition and long division, principles that are found in al-Khwarizmi's text written about 1,200 years ago. Next topic is the notion of algorithm. First, we have the input. Input is the information entered into a computer system. Next, we have the processing. The process of transforming input information into and output. In the processing, the problem should be identified first, and then it will be solved by the algorithm in the computer. Then lastly is the output, which is the visual, auditory, or tactile perceptions provided by the computer after processing the provided information.
Why study algorithm? Algorithm is the core of computer science. It is also the toolkit for analyzing and designing new problems. But the most straightforward reason for analyzing an algorithm is to discover its characteristics in order to evaluate its suitability for various applications or compare it with other algorithms. Put simply, we want to know how long an implementation of an algorithm will run on a particular computer and how much space will it require. Algorithm analysis is an important part of computational complexity theory, which provides theoretical estimation for the required resources of an algorithm to solve a specific computational problem. Usually, the efficiency or running time of an algorithm is stated as a function relating the input length to the number of steps known as time complexity or volume of memory known as space complexity. Lower bound is a very important part for any algorithm. Once we calculated it, Then we can compare it with the actual complexity of the algorithm, and if their order are same, then we can declare our algorithm as optimal. Let's discuss about the algorithm design strategies, which are the general approaches to the construction of efficient solutions to problems. Number 1. Brute force is a straightforward approach to solve a problem based on the problem statement and definition of the concepts involved. Number 2 and number 3, which are the divide and conquer and decrease and conquer, are somehow similar. Given an instance of the problem to be solved, split this into several smaller sub-instances independently, solve each of the sub-instances, and then combine the sub-instances solutions so as to yield a solution for the original instance. Number 4, which is the transform and conquer, is a method that works as a two-stage procedure. First, the problem is modified to be more amenable to solution. Second, the problem is solved. Number 5, the greedy approach is a solution constructed through a sequence of steps, each expanding a partially constructed solution obtained so far. At each step, the choice must be locally optimal. Example of this is finding the shortest distance in graphs. Greedy approach are mainly used to solve optimization problems. They do not always give the best solution. Number 6 is the dynamic programming. It is in contrast with the divide and conquer approach because divide and conquer is a top-down technique which logically progresses from the initial instance down to the smaller sub-instance. Number 7. Backtracking and branch and bound. Backtracking is usually without cost function. The main algorithm is as follows. Store the initial state in a stack. While the stack is not empty, it will read a node from the stack. While there are available operators, it will apply an operator to generate an instance. If the instance is a goal state, it will stop. If it is a new state, then push the instance into the stack. Lastly, number 8, which is the space and time trade-off. Space and time trade-off is inversely proportional because you can decrease the time complexity of your algorithm in exchange for greater space or consume lesser space in exchange for slower executions.
So here are the basic issues related to algorithms. First is how to design algorithms. I'd like to give you 2 examples, though there are many ways to design an algorithm. Insertion sort uses an incremental approach, and another approach to design is the divide and conquer approach, which is a recursive structure to solve a given problem. Second, how to express algorithms. There are 3 general and very common techniques to express algorithms, such as flowcharts, Nasus-Gneiderman diagrams, and pseudocode. Improving the correctness of algorithms. The algorithm is correct if for any legal input it terminates and produces the desired output. Automatic proof of correctness is not possible, but there are practical techniques in rigorous formalism that help to reason about the correctness of algorithm. In testing the efficiency of algorithm, there are 2 ways of checking its analysis. First is theoretical analysis. It uses a high-level description of the algorithm instead of an implementation. It allows us to evaluate the speed of an algorithm independent of the hardware or software environment. Second, the empirical analysis of the algorithms. Sometimes the mathematical analysis of efficiency is too difficult to apply. In these cases, the empirical analysis could be useful. It can be used to 1. Develop a hypothesis about the algorithm's efficiency. 2. Compare the efficiency of several algorithms designed to solve the same problem. 3. Establish the efficiency of an algorithm's implementation. 4. Check the accuracy of a theoretical assertion about algorithm's efficiency. Lastly, for the optimality, assumes knowing the future. Can you think of it? Replace the page that will not be used for the longest period of time.